Now I invite Pierre-Jérôme from STMicroelectronics to present an overview of STMicroelectronics semiconductors technology for RF applications.
Okay, so good morning, everybody. So I will present you an overview on the RF technologies from ST. Many in a perspective of high-capacity telecommunication systems. So in these perspectives, sorry, we have some figures of merit for this kind of high-capacity telecommunication systems, which are, as you perhaps know, there is a famous law, which is the Shannon's law, which describes the main parameters for this, which are the number of antennas, which has nothing to do with the technology. It's just system-based, it's purely system design. The bandwidth, as it was said by Nordams before, the bandwidth allows you to put multiple frequency channels, and so you multiply also the capacity of the system with respect to the data bit per second. And this is linked to the system design, but also this is also linked to the technology. So technology starts to be interesting for the bandwidth, and to get a high bandwidth, you need high frequencies. It was also said by Nordams before. And then there is a third parameter, which is of importance, is the signal-to-noise ratio, which allows you to find out the signal within the different channels and the different modulation you can use. So this signal-to-noise ratio is also depending both on the system and the technology. So with all these three figures of merit, we'll find what could be the best technology to fit your system, the telecommunication system design. There is an extra parameter, sorry, to keep you on this slide. I should have prepared this slide before, but I missed it, so I discovered this morning. So an extra parameter of importance is the switching speed of the transistor device we use for the switches, because you have to switch from frequencies to frequencies within the bandwidth. And a figure of merit on this one, and you will find it in the next slide, is what we call the R on, the resistance on state of the transistor, so to flow the electrons through the channel of the transistor. When you apply a signal on the gate, the electrons then should flow when the transistor is open. And the R1 is not alone. The capacitance in standby mode of this transistor is also important because it is the speed of opening the gate of the transistor. So the product R1 C off, also expressed in femtoseconds, then is of importance for the applications which need some switches. So let's go now. Sorry to bother you with all these preliminary figures of merit description without slides. So we have a bunch of technologies at ST. So first is the RF SOI semiconductor technology based on SOI wafers with silicon. The BiCMOS technology, which are using silicon germanium bipolar transistor with standard CMOS based for digital part or analog also devices. Then we have also the RF28 FDSOI, the well-known FDSOI semiconductor from ST, based on Soitec wafers as the RF SOI above. And then we'll have a summary of these technologies and how to access the technologies. So, sorry, it's difficult for me to see all this. So, for SOI wafers, this is a kind of roadmap looking back to the 2000 years here. So I will not explain all this history, but it's just to tell you that ST has a long history with RF SOI CMOS. So we are using, I will take this stick here. We are using high resistivity and trap-rich wafers from Soitec, as it was described by François yesterday. The CMOS technology nodes are ranging from 0.13 micron here, 130 nanometer, down to 40 nanometer to the latest one. And we can add on these technologies ultra-thick copper layer to be able to have very high quality inductances. You have here the 300 millimeter production, 300 millimeter RDI here. So you can see we have 65, and the last one is 40 nanometer in development. You have the 200 millimeter technologies here. You have the RNC off here in femtoseconds. So the values are in the black box here, black boxes. And the FT max, so that the maximum frequency, the cutoff frequencies. FT is just for the voltage or current cutoff, and F max is with the product of it's a power, in fact. So it gives you normally the F max is better than the FT because you have two parameters taken into account. So the IPCEI took care of these technologies here. So you see we have the whole nodes here for 5G sub-6 GHz, so that's infrastructure mainly, connection to network here, and 5G millimeter wave technology here, which is under development right now. You have the frequencies here, you have the RNC of values here, so it gives you an idea of the performances of these technologies. So, why choosing the RF SOI technology? Merits of these technologies is the switching speed, also the analog signal integrity, the quality of all the analog devices, and the low noise of the technology. So, important for the signal to noise I described before. With respect to availability of the technologies, so first, this one has two flavors. High performance here, we are quite right now. We are developing right now, but no prototyping before, not next year even, the year after, 2024. This one right now we are prototyping. So it's a little bit. It's a good technology even, but with not so high performances. And we have then a volume production for the 65 nanometer SOI FEM and the 40 nanometer in 300 millimeter here. The prototyping should happen beginning of next year only. So you cannot access to the technology before the prototyping is somewhat open. Then go to the BiCMOS, so same story, green for 300 millimeter, gray for the 200 millimeter. These BiCMOS technologies are very good for the FTF max. You can see the values here going up to 400 and 500 due to the fact that the bipolar transistor can be engineered separately for the CMOS, and it's a very specific device which enables this kind of speed. Even we think this kind of SIGE device can go up to 700 gigahertz later on, and even higher, but not so high that INP in the future, I would say. But it's not so expensive technology, so it's as expensive as the previous RF-SOI technology as showed before. So it's a very interesting technology. So IPCEI has been busy with this one. A little bit industrialization of this technology, but I didn't put this as it was not on R&D. And we had a very successful project which was called Taranto, finished last year with all these partners here, French, German, Italian partners. This project enabled ST to develop this technology and start the development of this one. It was awarded by the Excel GU in 2020. So it was a very nice collaboration between the partners here. So merits of this technology for the noise, it's the best one among the RF-SOI, BiCMOS, and FD-SOI. So if you need for satellite communication, especially very low noise value, it's a choice. It's a technology of choice. The output power is somewhat good, not as good as GaN or INP, for example, but it's better than the other ones. And the speed is very, very good as well. It's better than the other technologies. Okay, so here the roadmap. So these two technologies are in volume production at tested. It's not easy to access, I would say. It's possible, but we have to look at the requests. And this one should be ready for prototyping end of next year. So the B55X will be at the end the mainstream technology for ST, because we are investing a lot in Crolles with the extension of the capacity of the fab, for many reasons, but this is one of the reasons we are investing. Okay, then we jump to 28 nanometer FD-SOI. So the base volume production here in ST is made on the 28 standard FD-SOI technology. We had some modeling and some devices for RF analog up to 30 gigahertz here. We are right now prototyping also in 60 gigahertz. So I should have added a green bar somewhere for the 60. We are volume processing for the LEO and GEO space applications. And we want to push this RF analog up to 110 gigahertz here with very low consumption, very good power, performance here, and produce a new version of the space GEO. And this should be ready for prototyping right now. So, merits of the FD-SOI technology is the digital density possibility. The power output is good, and the noise level is as good as the RF-SOI technology. Okay, these are the the takeaways. I will leave you read at this. I will not read all this. I think that was clear. It should be. You should be able to select the right technology for your needs. Then I have a slide on the access to the technology. I would say that we had experienced a very difficult year this year because we had some issues with our an organization who is taking care of all these runs for accessing the technology. It's now solved. We are increasing the. It will be ready. This new organization will be ready by the end of this year. Should go. It should be more powerful next year. We should have a better situation, and we should be able to supply this kind of runs, 2 MPW runs per year for these technologies, 28 FD-SOI, BiCMOS 55X and BiCMOS 55. So I hope this should be available as well again. Normally they are sharing the same mask set, but after the technology roads are somewhat different, but should be possible. These are set as priority for the new organizations to start with. And then we should have some opportunity for the BiCMOS 9MW. This is 200 millimeter here. The other ones are 300. This one is a 300. This one is a 200. And so we should offer also some runs, not so often as the previous technologies. And then if you need these technologies here, H9 SOI FEM or SOI MMW or BiCMOS 9MW with high resistivity substrate, please contact your ST representative in Sweden. That's all.
Thank you very much, Pierre-Jérôme from STMicroelectronics.